You're tuning into the deep dive today because you want to get smart fast about what makes your Android phone tick, specifically those hidden sensors inside and how they connect to keeping your digital life secure.
Exactly. And you've brought together some fascinating pieces for us to explore today. We've got the lowdown on the different types of sensors crammed into these devices.
Yeah.
How apps actually, get their hands on that data.
Right.
A really cool tool called Firefox that lets you play with them yourself.
Oh, cool.
And the crucial security measures Android uses, like app permissions and digital signatures.
So the mission today.
Yeah, our goal is really to unpack all this so it's clear, engaging, and hopefully really shows you what's important without getting too bogged down.
Okay, so let's dive right into these Android sensors then. It turns out any app you download can potentially tap into the sensors your phone has.
That's pretty much it. It all goes to something called the Android Programming Interface. Think of it as the official rulebook for how apps and the phone's hardware talk to each other.
A rulebook, okay. And there are quite a few sensors, aren't there?
Oh, absolutely. There's a surprising number packed in. You've got the accelerometer, which measures movement in 3 directions, X, Y, and Z.
Like when you tilt the phone?
Or jerk it suddenly, yeah. Then the ambient light sensor figures out how bright it is around you.
For screen brightness.
Exactly. And the proximity sensor knows when something is close to the screen, like your ear during a call, so it turns the screen off.
Right, that makes sense. And there are more.
Oh, yeah. There's the compass, or magnetometer, telling you which way is north using magnetic fields, again on X, Y, and Z axis.
Okay.
The gyroscope detects rotation if you spin your phone. That's it in action.
Different from the accelerometer, then.
Totally different. Accelerometer is linear motion, gyroscope is rotation. Then there's the gravity sensor, which, always knows which way is down no matter how you're holding the phone.
Useful for screen orientation?
Precisely. And for the, let's say, weather buffs, there's often a pressure sensor to measure atmospheric pressure.
Like an altimeter.
It can be used for that, yeah. And sometimes a temperature sensor for the ambient air temperature. It's like a little Swiss Army knife of environmental awareness in your pocket.
It really is. So how do apps actually get access to all this constant stream of information?
Well, it's all managed by a central hub called the Sensor Manager. Think of it as the phone's sensor control center.
Okay, the sensor manager.
To start using any sensor, an app first needs to get permission, or rather, get a reference to this sensor manager.
How does it do that? Is there a specific command?
Yep. It uses a specific request to the Android system, a method called get system service.
Yeah, system service, got it.
And it passes a constant context.sensor service. That's kind of the official handshake, as you put it earlier.
Right. So the app asks the system for the sensor service. What happens next? Does it just get a sensor?
Good question. Sometimes a phone might have more than one sensor of the same type, maybe a couple of different accelerometers for different purposes. In those cases, Android usually designates one as the main or default sensor.
Okay, so if an app just says, give me the accelerometer, it gets the default one.
Usually, yes.
But what if it needs a specific one, or just wants to know about the default?
That's where the get default sensor method comes in handy. This method needs to know exactly which type of sensor the app is looking for.
And how does it specify the type?
That's where these handy shortcuts, or constants, come in. They're defined within the sensor class itself, acting like specific labels for each type.
Okay, labels. Can you give us the rundown? What are the main ones?
Sure. So if an app wants the accelerometer, it uses type accelerometer.
Makes sense.
For the ambient light sensor, it's type light. Proximity is type of proximity.
Right.
The compass goes by type of magnetic field. For the gyroscope, it's type of gyroscope, and gravity is type of gravity.
Okay.
Then we have type pressure for the pressure sensor, and finally, type ambient temperature for that temperature sensor we mentioned.
Wow, okay, so it's a pretty clear system. Type light for brightness, type paperscope for rotation.
Exactly. It's a really organized way for apps to say precisely what kind of data they need.
So what if an app wants to see all the different light sensors, maybe if there are multiple? Or just get a complete list of every sensor available on the phone?
Yeah. For that, there's the get sensor list method.
Get sensor.
If you give it one of those type constants, like type light, it'll hand back a list of all the light sensors on the device.
Okay.
And if you want to see absolutely every sensor of the whole shebang, you can use the special constant sensor.typeal.
Sensor.typeal. Good to know. Okay, so apps know how to find the sensors, but how do they actually get the live feed of data? Does the app constantly have to ask?
No, that would be really inefficient. It works through something called event handling.
Events.
Yeah. When a sensor detects a change, say, the accelerometer detects movement, it fires off an event. Apps that are interested in that particular sensor need to sign up or register to receive these events.
Like subscribing to updates.
Exactly like that.
Yeah.
This is done using a sort of listening interface called Sensor Event Listener.
Sensor Event Listener. Okay.
It has two key methods, or callbacks, that the app needs to implement. One is on sensor changed.
Makes sense, called when the sensor value changes.
Precisely. That's where the app gets the actual new data. The other one is on accuracy changed.
Accuracy. Why would that change?
Well, sometimes the sensor might need calibration, or there might be interference affecting its readings. So this method lets the app know if the reliability of the sensor data has changed.
I see. So if my running app wants to track my steps using the accelerometer, it implements the sensor event listener.
Right.
And then the on sensor changed method gets called automatically whenever the accelerometer detects movement.
You've got it. To actually start this listening process, the app uses the register listener method of the sensor manager we talked about earlier.
Back to the sensor manager. Okay,
Yeah.
register listener. What does that need?
It needs three main things. First, a reference to the part of the app that implements that sensor event listener interface, the part that's actually doing the listening. Second, the specific sensor object they want to monitor, like the default accelerometer sensor we got using getDefault sensor.
Right.
And third, a setting that tells the system how often they want to receive updates, the frequency.
So that's how they control how frequently they get new information? That seems important for battery life.
Hugely important.
What are those frequency settings?
There are a few standard presets defined right in the sensor manager class. Sensor delay normal is, well, normal. It tries to find a good balance, maybe updates a few times per second. It even adapts to things like screen orientation changes.
Okay, balanced. What else?
There's sensor delay fastest. That means give me the data as fast as the hardware possibly can.
Sounds battery intensive.
It definitely can be.
Yeah.
Then there's sensor delay, which is tuned for smooth user interface updates, a bit faster than normal usually.
Right.
And sensor delay game, optimized for the quicker responses that games typically need, even faster.
Game, UI, normal, fastest.
Got it. And interestingly, if an app has very specific timing needs, it can actually skip these constants and provide an exact update interval in microseconds.
Wow, really fine-grained control.
Yeah, lots of flexibility.
So when that on-sensor change method is triggered, it gets called with some information. You mentioned it gets the data.
Yes, it receives an object, a sensor event object.
Sensor event. Okay.
And that sensor event is where the actual sensor data lives. It tells you which sensor triggered the event, just in case you're listening to multiple sensors with the same listener.
Handy.
It contains an array of floating point numbers called values, and these are the actual readings. For the accelerometer, this would be 3 values, the acceleration forces along the X, Y, and Z axes.
The raw data.
Exactly.
Right.
It also includes a timestamp, which is like a precise time code, in nanoseconds of when the reading was taken.
Nanoseconds. Wow.
Yeah, very precise. And finally, an accuracy rating telling you how reliable that specific measurement is, using constants like sensor's texture accuracy, high or low.
Okay, so the app gets the sensor, the values, the time, the accuracy. Pretty comprehensive. Now, what happens when the app is done? Say, I close my running app. Does it just keep listening in the background?
No. That's a really, really critical point. It's absolutely crucial for apps to stop listening to sensors when they no longer need the data.
How do they do that?
They use the unregister listener method of the sensor manager. They basically tell the system, okay, I'm done with the sensor now.
And if they forget?
Forgetting to call unregister listener is a classic way to accidentally drain the user's battery. The sensor keeps running, sending events, consuming power, even if the app isn't in the foreground.
Ouch. So good app developers need to be really careful about that. Makes perfect sense. Got to be responsible with those resources.
Absolutely.
Now, shifting slightly, you mentioned an application called Phyphox earlier. What's the story there?
Right, Phyphox. Phyphox. It's a really neat app, actually, especially if you're curious about what's really going on inside your own phone.
Right.
It was created by the RWTH Aachen University in Germany, and it's basically designed to let you explore and visualize the data from almost all the different sensors that your phone or tablet has.
So you can see the raw data yourself.
Exactly. You could see live graphs of the data coming in from the accelerometer as you tilt your phone, watch the gyroscope readings change as you spin it, see the light sensor react when you cover it with your hand. Pretty much everything we've just been talking about.
That sounds like a fantastic way to get a hands-on feel for this stuff.
It really is. It takes it from abstract concepts like type accelerometer to something you can actually see and interact with. great for learning or just pure curiosity.
Cool. I might have to check that out. Okay, so we've got all these sensors doing their thing, apps tapping into them, potentially draining battery if they're not careful.
Right.
Now let's switch gears a bit to the flip side of our discussion, security. You mentioned that mobile devices are becoming bigger targets for attacks, much like regular computers.
Yes, that's a really important point to make. While maybe, say, 10 years ago, you might have thought of your phone as relatively safe compared to your laptop.
Yeah, I probably did.
The sheer amount of personal, sensitive data we carry on these devices, now contacts, messages, location, banking apps, makes them incredibly attractive targets for malicious actors.
That makes sense.
And unfortunately, those very sensors and communication technologies we rely on can become potential avenues for exploitation.
How so? I mean, I get how maybe accessing my contacts is bad, but how can, say, Bluetooth become a risk related to sensors?
Well, it's often not the sensors themselves being directly hacked in isolation. It's more about how malicious apps might abuse the permissions they have to access these technologies in combination with sensor data or other info.
Okay, explain that.
For example, an app with Bluetooth permission could potentially scan for and try to connect to other nearby devices without your explicit consent in that moment, maybe to try and transmit stolen data or even push malware. Similarly, if a malicious app gets permission to make phone calls, this CalPhone permission, it could potentially dial premium rate numbers in the background without you knowing, racking up huge charges.
Oh, nasty.
Messaging permissions like send SMS could be abused to send spam or, again, messages to premium services. Wi-Fi access could be used nefariously to connect to unsecured networks and try to intercept your data traffic.
Man.
And even NFC, which we use for contactless payments, could theoretically be exploited for unauthorized transactions if a rogue app somehow gained the necessary permissions and found a vulnerability.
Okay, that's, a little unsettling to think about all these connections. And what are some of the common, nasty things these malicious apps actually do if they get onto your phone?
Oh, the list is unfortunately quite varied. It can range from the simply annoying to the seriously damaging.
Like what?
You might get bombarded with annoying pop-up messages or ads, sometimes even showing up outside the app itself. The app might open unsolicited web pages in your browser.
Adware, basically.
Adware is common, yes, but it can get worse. Generating those unexpected costs through unauthorized calls or premium SMS messages we mentioned.
Right.
Stealing your personal information logins, passwords, financial details for fraudulent purposes. Identity theft is a real risk.
Yeah.
And even tampering with the data stored on your device, like reading, modifying, or deleting your text messages, your call logs, or your contacts.
Yikes. Okay, so apps can potentially cause a lot of headaches and much worse. But I know that operating systems like Android aren't just, sitting ducks, right? There have to be security measures baked in.
Absolutely. That's crucial. Modern mobile operating systems, Android included, have multiple layers of safeguards designed specifically to try and limit the damage that malicious apps can cause.
How do they do that, generally?
A key way is by controlling what actions an app is actually allowed to perform. Can it read your contacts? Can it write to your calendar? Can it access your messages? Can it send an SMS? Make a call? Track your precise location? Access the internet? Read or write files on your phone's storage?
So it's about limiting capabilities.
Exactly. While the specific implementation details might differ a bit between, say, Android and iOS, the fundamental goal is the same. Enforce limits to minimize the potential for harm if a user accidentally installs something bad.
And you mentioned Android is built on Linux. Does that help with security?
Yes, that's a significant advantage. Android inherits the core security principles of the Linux kernel, which has decades of development behind it. This includes its robust file system permissions, its security rules governing access to system resources, and, really importantly, its mechanisms for isolating applications from each other.
Application isolation, what does that mean exactly?
Think of it like this. Each Android app runs in its own separate sandbox. It has its own little space to operate in with its own resources.
So every app is kind of in its own protected container. It can't easily mess with other apps.
Precisely. That's a cornerstone of Android's security model. And a huge part of enforcing this isolation and protecting the user is the permission system.
Permissions. We hear about those all the time when installing apps.
Exactly. Any app that wants to access potentially sensitive functionalities like reading your contacts, using your camera, getting your location, sending an SMS, basically anything that could impact your privacy or cost you money must explicitly ask for your permission first. The user has to grant it.
And where do the app developers actually state, my app needs these specific permissions?
They have to list every single permission their app requires in a special configuration file that's bundled inside the app package. It's called the Android manifest.xml file.
The Android manifest, okay.
Yeah. And the names of these permissions are generally designed to be informative, or at least understandable.
Yeah.
The idea is that when you see the request, you have a decent idea of what the app wants to do.
Can you give us a few examples of these really important Android permissions? What are some common ones we might see?
Sure. There's read contacts, which, as it sounds, allows the app to see your list of contacts.
Okay.
Then there's write contacts, if it needs permission to add or change contacts in your address book.
Mm-hmm.
Similarly, you have read calendar and write calendar for accessing and modifying your calendar events.
Calendar access.
For messaging, there's the powerful sends MS permission to let the app send text messages directly. Read SMS lets it read your incoming and outgoing texts.
Whoa, read SMS sounds sensitive.
It is. And there's also write MS, which technically allows an app to create draft messages, but they usually still need your final tap on send before they're actually sent.
Okay. What about network and storage?
The internet permission is absolutely essential for almost any app that needs to connect to online servers, fetch data, log you in, etc.
Very common.
Then read external storage and write external storage control access to files on your phone's shared storage, like photos, downloads, and other documents. Though this is handled a bit differently in newer Android versions with scoped storage.
Ah, okay. And location.
A big one is access find location. That gives the app permission to pinpoint your precise location using GPS. There's also access course location for less precise network-based location.
Right. So when you install an app and it pops up that list asking, allow app to access contacts, allow app to access location, that's the system showing you what's declared in that manifest file.
Exactly. That's the permission system in action, putting the user theoretically in control.
Now, you mentioned the app package and that Android apps are packaged as APK files. What's the journey an app takes to become one of those files? How's it built?
It's quite a transformation process, actually. It starts with the app's code, usually written in a language like Java or Kotlin.
Okay, the source code.
First, that code gets compiled into a more basic intermediate form called Java bytecode, stored in .class files.
Standard Java compilation.
Right. But Android devices don't run Java bytecode directly. So the next step is that these .class files are further optimized and converted into a different format called Dalvik executable, or .dex files.
DEX files. Okay.
These .dex files are specifically designed to run efficiently on the Android runtime environment. Finally, these .dex files, along with that Android manifest.xml file we talked about.
The one with the permissions.
Yes. And all the other bits and pieces the app needs, like images, sound files, layout definitions, text strings, are all bundled together into that single .apk file.
APK stands for?
Android package. It's basically a zipped archive containing everything needed for the app to run. That's the file you download and install.
Like packing everything needed for the app into one neat little suitcase?
That's a perfect analogy, yeah.
And you mentioned earlier that each app runs in its own virtual machine or sandbox with the unique UID. How does that contribute to keeping things secure technically?
That unique user ID, or UID, assigned by Android when the app is installed, is really fundamental to the isolation model.
Okay.
Think of it like giving each app its own individual security badge and a dedicated protected workspace, that sandbox environment, often leveraging the underlying Linux user separation.
So App A literally runs as a different user than App B?
At a system level, yes.
Yeah.
Because each app has its own UID and runs in this isolated process, it fundamentally cannot directly access the private files or memory space of other apps on the same phone. Its data is kept separate.
That prevents one rogue app from just reaching in and stealing data from my banking app, for example.
Exactly. It's a major security boundary. However, as we kind of touched on, apps can communicate with each other through defined Android mechanisms, like intents or services. And that inter-app communication, if not implemented carefully by developers, can still be a potential area of risk.
Right. So the isolation is a strong foundation, but not foolproof if apps talk to each other carelessly.
Correct.
Now, the last big piece of the security puzzle you mentioned is Android app signing. Why is signing the app so important?
App signing is absolutely vital. It serves two main purposes: authenticity and integrity, especially when you're getting apps from a central place like the Google Play Store.
Authenticity and integrity, what do those mean here?
Authenticity means you can be reasonably sure the app actually came from the developer it claims to be from. Integrity means you can be sure the app hasn't been tampered with or modified since the developer signed it.
Okay, so it proves who made it and that it hasn't been messed with.
Exactly. To be listed on Google Play, every single app has to be digitally signed by the developer using a special cryptographic key, a private key that only they should possess.
How do they get this key?
They generate it themselves, usually using standard tools like KeyTool, which comes with the Java development kit, or sometimes helpers like JarSigner. This key is stored securely in what's called a key store file.
And how does the signing process actually work in the real world, say if a developer is using Android Studio, the common development tool?
Within Android Studio, it's integrated pretty smoothly.
Yeah.
When a developer decides they're ready to release their app, they'll typically go to the Build menu and choose an option like Generate Signed Bundle APK.
Okay.
This kicks off a wizard that guides them through the signing process.
And I remember seeing something about that key store file needed here. What's that all about again?
Right, the key store file. It's like a secure, password-protected digital container or vault where developers store their private signing keys. They need this file and its password to sign their app.
So it's super important they keep that key store file safe and remember the password.
Absolutely critical. Losing the key store or its password can mean they can't update their own app on the Play Store anymore because they can't prove they're the original developer.
Ouch. What happens if a developer is launching their very first app and doesn't have one of these key stores yet?
In that case, Android Studio makes it easy. During that Generate Sign Bundle APK process, it'll offer the option to create a new key store. The system will guide the developer through choosing a secure location on their computer to save this new key store file and setting strong passwords, one for the key store itself and another for the specific key alias within it.
So once the key store exists, either new or existing, the app gets signed using the private key inside it.
Correct.
And that generates the final signed APK file that then gets uploaded to Google Play or distributed elsewhere.
It's exactly right. The APK file that's created after signing contains not just the app's code, the DEX files, and all its resources, but also that crucial digital signature information, usually tucked away in a meta-INF directory inside the APK.
And that signature is what Android and the Play Store check?
Yes. When you install or update an app, Android checks this signature against the public key certificate embedded in the APK. It verifies two things: that the app was indeed signed by the key corresponding to the certificate, and that the app's contents haven't changed since it was signed. If the signature is invalid or doesn't match previous versions, it's a major red flag that the app might have been tampered with or isn't legitimate.
Got it. So it's like a digital seal of approval and tamper evidence sticker all in one.
That's a great way to put it.
Okay, so, wow. To wrap things up then, we've taken a really deep dive into the fascinating world of Android sensors, the sheer variety of them, from accelerometers to light sensors, how apps can tap into them using things like the Sensor Manager and Sensor Event Listener.
Right, and the importance of managing those listeners carefully.
Yes. And how an app like Firefox lets you actually see all this in action on your own device. And then we pivoted to the critical security side, understanding the risks, but more importantly, the safeguards, like the Linux Foundation, application isolation, the permission system that tries to put users in control.
Giving you that choice, hopefully an informed one.
And finally, the app signing process that helps ensure authenticity and integrity, making sure you're getting the real deal, especially from places like Google Play.
That's a fantastic summary. It's easy to just use these phones day to day and overlook these seemingly small components and security features, isn't it?
Totally.
But when you actually dig a little deeper, like we just did, you realize just how much complexity and, frankly, ingenuity goes into making these powerful little devices work reasonably reliably and securely.
Absolutely. It's almost mind-boggling sometimes to think about all those tiny sensors constantly feeding data into our phones, allowing them to interact with the world and us in so many subtle yet powerful ways.
You know, this leads to a really interesting final thought, maybe something for our listeners to consider.
Oh, yeah.
Given the sheer number of sensors packed inside your phone, which we've just discussed, and thinking about the often quite extensive list of permissions that many apps request, what are some of the less obvious ways your device might be constantly sensing, interpreting, and maybe even learning about the world around you and, by extension, potentially gathering subtle information about you and your habits, even beyond the permissions you explicitly granted?
That's Yeah, that's provocative. Like, how is all that data potentially being combined or inferred?
Exactly.
Yeah.
It's definitely worth taking a moment to ponder the implications. Maybe even, take a look through the app permission settings on your own devices sometime and just see what's enabled. You might be surprised.
Definitely something to chew on. Thanks for joining us on this really eye-opening deep dive.